set of my favorite problems. As you well know, the problem set that was due today has been extended to Thursday. Problem set 5 will be out today. Now, what we're going to do is we're going to break down problem 1. We can look at number 4. And we'll look at number 8E. And I'll do the first one for 4. All right. Thank you. Thank you. Contrary to how I've been behaving, I act when appropriate. I've been, yeah. What's the combination of sassy and salty? Savage? Oh, ooh, good. I'll have to consult my my lexicon specialist. All right. First thing you do is you draw this thing up. What are we doing? We're doing physics. When? Right now. Why? Why not? There we go. This is homework problem set 1. Or I'm sorry, problem set 4. God, it's problem 1. Haha, right back at you. All right. Really what we want to know is we want to know the currents of going through resistors R3, R1, and R4. Basically the currents. And I'm big on, I just want to know the directions. Does it go left, right, right, down, up, down, bottom up, stuff like that. And what I do is I build my J's. J's will always be clockwise. And my loops, which will again always go clockwise. And the big point of this setup, or how we're going to set up the equations, is that we always start in the lowermost left corner and we go around and we measure all the potential differences in that circle. And the one thing that we know definitively, if you start and finish at the same place, the potential difference is 0. So for loop 1, that delta V1 is 0. Or actually, delta V would be sufficient since it's 0 anyway. And then what you do is you follow the path from there to there. I'm going with J1 across R2. So minus J2 R2. I'm going from there to there with J1 across R1. Minus J1 R1. Oh, I'm sorry. Thank you. So it's J1 R2. J1, R1, and yeah, that's the important part, because if you slip up right at the beginning, the whole thing just shatters and fans error out everywhere. There is probably the most difficult stretch because you're going with J1 across R3, but you're going against J2 across R3. And then you're going from there to there in the last part, positive to minus, so it's minus V1. So you're following all the rules that we've set up before. Across a battery, pay attention only to the leads. Across a resistance, with the current you go down, against the current you go up. And what I'm going to do right now is I'll simplify it. I'm going to take all my J1s and factor them out. Minus J1 R2 plus R1 plus R3 plus J2 R3 minus V1. And in one of the few moments where I actually say plug and chug is a good thing, this is it. So rather than slugging around all those R's and V's, plug in the letters right now, or plug in the numbers right now. 0 equals minus J1, R2 is 12, R1 is 6, R3, 42. R3, 42. V1, 18. So that leaves you with 0 equals minus J1, 18 plus 42, 60, plus J2, 42, minus 18. Now I'm really a big fan of common factors. They make the equations much more easy to handle. And like I said, it's the physics, not the math, that I want to understand, or understand if you understand it. So I'm going to divide everything by 6. And that's the loop equation for my first loop. Very easy to handle. All I did was apply the rules, set up the equation, simplify, plug and chug, and then get it to a point where I can handle it. Now we do the same thing for number 2.
You don't need to go ahead and get J1 complete by itself.
Not yet. We could. All right, fine. You asked. Let's do that. So 10 J1 is equal to 7 J2 minus 3. So J1 is equal to 7 J2 divided by 10 minus 3 divided by 10. Now I keep them separate because I'm lining them up because they're going to get divided anyway. So might as well do it right there. So set up loop 2. I start here. I go with J2 across R3. But I go with J1 across R3 as well. I go from negative to positive across V2, so it's positive V2. And then I go with the current on both of these with J2 across R5 and R4. So minus J2 R5 minus J2 R4. And so that gives me the next equation. Once again, factor. J2 R3, J2 R5, J2 R4 plus V2 minus J2 R5. Oh, no. That's the one I'm looking for, and it is positive. So factor out the negative J2 from R3, 5, and 4. The V2 comes down, the J1 R3 comes down. Yes. Now, plug it in. R3, 42, R5, 14, R4, 28. V2, 21. 42. Now add them all together. 60, 70, 84 plus 21 plus 42 J1. They're all divisible by 7. That's 12 J2 plus 3. Oh, I could do, it's not necessarily 21. Well, 42 divided by 7 is 6. But you could see there was also another factor of 3. So in fact, it was 21 that was the common divisor. Minus 4J2 plus 1 plus 6J1. And so that is, oh, 2. Thank you. So divide everything by 3. 12 becomes -4, or 12 becomes 4, 3 becomes 1, 6 becomes 2. Next, plug in J1 from over here. Distribute. That's 7/5 minus 3/5. So now what I'm going to do is I'm going to get my J's on one side, non-J's on the other. 4J2 minus 7/5 J2 equals 1 minus 3/5. Common denominator of 20. 5 times 4 is 20. 20 minus 7 is 13/5. J2. Oh, I'm sorry. That's not it. What's the 4 minus 3.5? 4 minus 2.6. 13/5. I cannot write this morning. 13/5 J2 equals 2/5. So J2 is equal to 2/13. And it's a positive 2/13. I would keep it in fraction form until the final answers. So J1 becomes 7/10 2/13 minus 3/10 and the numbers are kind of weird, but not too. -5/26. So the J1 is -5/26, and J2 is 2/13 positive. Okay. So now, if I just wanted the numbers, -192 milliamps and J2 is positive 154 milliamps. That means I1 is 192 milliamps in a counterclockwise direction. I2 is 154 milliamps, and it's running in a clockwise direction. If J is greater than 0, the current runs clockwise. If J is less than 0, the current runs counterclockwise. So negative J's are counterclockwise, positive J's are clockwise. Which means that the current on the left is negative and the current on the right is positive. Yes?
Can you tell the direction based on battery?
You can get a good idea. When I look at this, I see that this battery will produce a clockwise current. So most likely, sometimes not, J should be positive. This one, looking at this, says that the J value should be negative. It should produce a counterclockwise current. So the answer that you should get is negative, which is what we got. Now, a lot of students immediately say, well, I could just look at the batteries and then just flip J in the opposite direction and then rerun the equations. No, don't do that. It is a very simple process. The core task for this type of problem is to find your J1, J2 immediately. And do not deviate from the plan. J's are always clockwise. J's are always this current that is running clockwise. But the battery says, no, follow the instructions and you'll do fine. Here, we're identified with a positive on the right and negative on the left. That means the current going through the middle is awesome because both currents go in the same direction through that battery by visual inspection. If that's the case, I3 is equal to I1 plus I2, 192 plus 154, or 346 milliamps straight up. For the other currents, I1 and I4. Now I1, the way that I'm saying I1 in this particular case is that I1 is the current going through R1. Really, I should have written it as those dreaded capital I's, but I know what you're talking about. I got to remember to tell the graders how to grade this. This big I1, which was listed in the box as little I1, is just the current running through the battery. And I want to know, is the current running from left to right or from right to left, and with what magnitude? Well, I1 is there, or R1 is there. It's running in a counterclockwise situation. So the current big I1 is 192 milliamps right to left. I4,
is it okay if we put like counterclockwise?
for this particular, if I'm looking for the current of the resistor itself, I'm looking for current magnitude and current direction. When you're thinking only about an individual resistor, you're only thinking about it in a linear sense.
If it's negative, is it always going to be right to left?
No, because down here it's from left to right. Same current. Now I4, the current is running clockwise through it, and it's running from right to left because down here its current's there to there. So it's 154 milliamps right to left.
That's supposed to be I2.
This is, I2 is the magnitude of J2. I4, which was specifically asked in the problem, is the current running through R4.
So if you were to ask for the resistor strength at one of those currents, would you just use Ohm's law and use that particular?
If I asked for, like, I think the question you're asking is, if I was to require what's the voltage drop across that resistor, yeah, not the resistance strength, then I would say yes. Then you've got the current going through it, you've got the resistance, so you can figure out the voltage drop from there. Yes.
You figured up I3, why didn't you use the negative 192 instead of
I3, the whole subtlety behind using J's and I's was that for some particular reason, after several many years, they still want I to always be positive. And with J1 and J2, I call those the current velocity. They're allowed to be negative or positive. The I's I call current speed. Because they're running in a particular direction, the current runs like this. So I don't care about positive or negativeness of everything. All I know is A, it's going up in the middle, and B, they're both going in the same direction. So what I did is I just took the magnitudes of both, put them together, and then I got it. Now if it was going, oh, I can't do this. Like this, ooh, I keep going. See, when they pass through the middle, one is going down while the other one is coming up. So you have to make sure, it doesn't really matter what signs they are. All that matters is you understand which is the big one and which is the small one. If the little one is the one going up, then it's up. If the big one's the bully, then it's going down. And so it's kind of I kind of pull away from the math and I let logic and I want the logic and reasoning behind it to reign over everything.
This problem, you're asking for little I3 and then big I.
Well, I would say, yeah, if I was to rewrite this question to be more appropriate, like in a test, I would say, I would probably just write, give me capital I3, capital I1, and capital I2. Or capital I3, capital I1, and capital I4. The current's running through each of those resistors. You would still look for your J's, capital J's, or I'm sorry, your little J's, and then you look for your little I's. Once you got your little I's, and the rest just goes down.
Is it like the little eyes and big eyes, they're different? Or can they?
The big I, yeah. I use the little I's are the current loops themselves. And they're actually the current speed. The J's are the current velocities. The big I's are, well, the current going through that resistor is in what direction? Tell me what it is. And some people do, like, we're getting bogged down in the nuance. Let's say J was -2. So I would equal 2. So some types of problems, they ask for I, mag, and direction. So in this particular case, it would be 2 to the left. Now, some of them intentionally just write, give me the value of IM, or I'm sorry, just give me the value of I. Since the current runs counterclockwise and that I axis is going up, that I would be -2. What I like to do is, in order to reduce confusion, play with magnitudes only, and then use reason to figure out everything else. All right, and that is Kirchhoff's law. And it will be on the test. All right, number 4. And really what I'm going to do is, I'm going to talk about 4. Okay. Last week, we talked about the particle going into a magnetic field. And a particle feels a force that you use this to determine the direction of the force. And in this particular case, particle A, I'm going to have to use A and B. Particle A goes off to the right and crash lands here. And they say that that distance is 4 meters to the right. And this is circular, though it's drawn horribly non-circular. The velocity of the particle, of all the particles, is 1,000 meters per second. The charge of A is positive 10 times 10 to the negative 9th coulombs, and the mass of A is 2 times 10 to the negative 9th grams. And I've been, which means this is 2 times 10 to the negative 12th kilograms. So you need to have the masses in kilograms. Now, the force that we use in terms of magnitude is this. Force is equal to QVB. For this vector, the way that we use it, V direction, magnetic field direction, and charge. That charge, as far as we're concerned, is positive or minus. So this has a velocity vector that looks like this. Now, what it did is it entered the region of the magnetic field and it banked right. Which means that it experienced a magnetic force to the right. We only have 2 choices, out or in. If the magnetic field was into the board, hand is in the direction of V, B goes into the page, B, the force of magnetic field goes to the left, which is not what we want. So the only other way to do this, you're just going to have to go through both choices. V field goes that way, B field goes up, magnetic force to the right. So the B field has to be up out of the page. Now I am given, what really is going on here is that this is a circle of radius r. if the distance from there to there is 4 meters, what it's really saying is that not the circumference, but the diameter is 4. So the radius is 2. We're dealing with a circular motion. So sum of the forces is equal to mv squared over r. There is only one force acting on this, and that is the magnetic force, QVB. So the V's, one of the V's cancels. And all I'm really looking for now is the magnetic field strength. MV over R, Q is equal to B. 2 times 10 to the negative 9th, 1,000. 7 times 10 to the negative 9 times R, which is 2.
Isn't your mass to the negative 12?
Excuse me?
Your mass, you said it was
10 to the negative 12. Thank you. That helps. Oh, that helps so much. Because I was about to get a B field strength that was obscene. And I get 1.42 or 1.43. Calculator people.
MV squared over R is what value, or what?
MV squared over R is Newton's second law in circular motion. So rather than sum of the forces is equal to MA, A in this case is V squared over R, circular motion. Hence, sum of the forces is equal to mv squared over r. That one force, what is the force? Well, it's the force in a magnetic field, QVB.
I got 0.143.
0.143, that could be it. Double check that. I may have been off by factor of 10. Point 143?
It's 1 7. Because that thing can't stop at 7.
Oh, that's right. I was being sneaky. Because 10 to the negative 12 times 1,000 is 10 to the negative 9. 10 to the negative 9 divided by 10 to the negative 9 is 1. 2 divided by 2 is 1, so the answer is 1/7 of a Tesla, which is entirely legitimate. So that's the magnetic field. The magnetic field is out of the page with a magnitude of 0.143. Question?
Where did we get the R?
R was given because I told you that the distance from there to there was 4.
Why is it in the formula we're using? Why is it the equation?
Because the motion of the particle is circular. It's wandering along on its own, minding its own business. It enters the magnetic field. It then proceeds to move in a circular motion. That circle has to have a radius. That radius is r. Now, it came in there, it landed there, that's the diameter. So if the diameter was 4, the radius was 2.
Is it always within a circle, or sometimes could it just be a arc?
If it is, it's circular in nature, it may not move in a full the way that it moves is circular, yes. The only way that it wouldn't be circular is if there was a secondary weird field going on. No. That would be bad.
Why are we using B? Is that just
B is the number, B is the unit, or not the unit, the variable expression for magnetic field.
okay?
It's not my fault. I would have used capital M, but no, or T. for Tesla for magnetic field, but no, the jerk who, well, not jerk, he probably won Nobel. No, he didn't win Nobel Prizes. He was dead before then. He created 4 values. The magnetic field was the second one, and he was just being alphabetical. And it's just B. It's just B. There's no, not like impulse, P impetus, P momentum. B is just B. I mean, he just picked it out of thin air. I'm not pleased with that. So looking at part B for this, I'm given a new mass, (20 times 10 to the negative 12 kilograms. I'm given a new charge, (-7 times 10 to the negative 9th coulombs. And then what I'm going to do is I'm going to look for that distance where it lands. Now, in both cases, the positive and the negative charges, the velocity goes that way, the B field goes out of the page, V cross B is always to the right. However,
Is that only because of the drawing?
only because of the drawing, yes. And the Q is negative. V cross B for positive charges, you just leave it like that. V cross B, negative charge, you flip it over. And so now it's going that way. The negative particle will go in a different distance. Now what I'm going to do is I'm going to use this equation here, and I'm going to solve for R.
This is MB is 20 times 10 to the negative 12. So
Mm-hmm. And since I'm really looking for diameter, and we do the same thing. 10 to the negative 12 times 1,000 is 10 to the negative 9. 10 to the negative 9 divided by 9 is 0. 0.143 is 1/7. That kicks it up to the numerator. That numerator 7 cancels with that denominator 7. So those go away, and I'm left with 40 meters. And I think that's the answer for that. And then you lather, rinse, repeat on C and D. Okay. Now for the last one,
How do you want to know where the direction is?
how do I know where the direction?
Like the central and then the base.
Say it again?
Like it says, on that part, it said in what direction is the magnetic field, you just want like a little circle with the dot.
Yeah, you just say the magnetic field is out of the page, circle dot.
would you not put -7 in the
When you're dealing with that, I only care about magnitude. All right, last part.
Wait, so you don't divide by the 7? The actual.
I did, but what happened was, what did we talk about what 0.143 is? It's 1/7. 1/7 in the denominator becomes a 7 in the numerator, which cancels with that.
Do we
I
not
mean-
need to say -40, since it's moving to the left? It's-
What? Ooh, hold on. You've asked for subtlety. Where I would say, okay, fine, fair enough, 40 meters to the left. And that would be it. Now, problem 8C, there's a story behind this. I learned it when taking physics as an undergrad. And then the TAs told me what I'm going to tell you right now. Don't freak out at this. It's not that bad. It's a lot like I'm about to bring in a a velociraptor, but the velociraptor is in a cage. It's been heavily sedated. It's just going to lie there at the bottom of the cage. You can't get hurt. So you can just look at this problem and go, ooh, it looks so hard. No, it's not. I want to know the B field at that point. The radii are 0.1, 0.2, 0.3 meters. The current running through all this stuff is 0.3 amps. The current magically appears here, goes over there, and over there, where it disappears and magically goes away. The question I want answered is, what is the B field in the center of those arcs? Could I ask the B field anywhere other than the center of the arcs? Yes, but it would cause intense crying, so I'm not going to ever do it. It will only be at the center of the arcs. Each of these B fields produce their own B field. The major ones, the first and the third, they're having counterclockwise currents. The one in the middle is producing a clockwise current. Counterclockwise currents produce B fields that are in above it and B out below it. Using our wrap rule again, they go out at the top and in at the bottom. So the B field created by 1, since it's counterclockwise, it will produce a positive B field. The B field for 2, since it is clockwise, will produce a negative. And the B field for 3 will be positive. So the B field at these points, at this specific point, sees a positive from the inner, negative from the middle, positive from the outer. Now for an arc, arc's magnetic fields are mu naught I theta over 4 pi r. The total B is B1 plus B2 plus B3. B1 is a positive value, mu naught I theta 1 over 4 pi r. B2 is negative, mu naught I theta 2 over 4 pi r2. The last one, positive.
B1 and B3, the same picture drawing, since they're like
Yes.
the same.
Mm-hmm. Now, the first thing I would do is factor out some common factors. Mu naught I of 4 pi theta 1 over r1 minus theta 2 over R2 minus theta 3 over R3. I'm sorry, yeah. There we go. And now we plug and chug. U naught 4 pi times 10 to the negative 7, I believe. 4 pi. I is 0.3. These arcs are semicircles. What is the semicircle for an arc? Or what is the radians? It's pi. Semicircle radians are pi radians. So pi over 0.1 minus pi over 0.2 plus pi over 2 times 0.3. The radians for a quarter circle is pi over 2. And then we plug all this stuff in. I would probably factor out a pi right now. Now, B fields can be positive or negative. That's okay.
Why do you have 2 times 0.03?
Because that theta is pi over 2.
If you not I, where do you get the value for that?
Where do I get the value for I? I gave it to you.
The
Oh, mu naught is a constant.
Wait, can you repeat why you did it 2 times 0.3?
Theta 3 is associated with not a semicircle, but half a circle. What's the arc for half a semicircle? Pi over 2. I'm sorry, half of a semicircle is quarter of a circle. So, full circle, 2 pi. Half circle, pi. Half of a semicircle, pi over 2. Or quarter circle, pi over 2. And I get that. Yes.
The pi on the second, right above the answer, you cross out 4 pi over 4 pi.
But all those pi's factor out.
All right, yes, sir.
All right. Yeah. Any other questions? Yeah.
Where are we getting that N equals MV squared over R from?
MV squared, circular motion. 213. All right. Class on Thursday. New problem set will be available then. No tutorial on Friday. Friday before spring break. What are you doing on? You should be going out. Nothing. Just go away. If it's positive, it's out.